Hi, welcome back. Today we're going over section 3.9, which is titled Derivatives of Inverse Functions and Logs. And I'd like to start out with just a refresher on what an inverse function is and some of the notation for it. So let's say I have f of x is equal to 6x squared plus 7. Let's go ahead and say that's what it is. Now, if I wanted to find the inverse function of f of x, I would notate it like this. It would be f minus 1 of x. So that minus 1 up there represents the inverse of f of x. Now, how do we find an inverse? Well, what we do, so let's go ahead and call f of x y, just to make it a little easier to write. So y equals 6x squared plus 7. Well, to find the inverse, we flip-flop where the y and the x are. So where there's a y, there's now an x, and where there's an x, there's now a y. Then the next step is to solve for y, to find the inverse of f of x. So we would subtract the 7 over, minus 7, divide by the 6, divide by the 6 equals y squared. And then we would take the square root of both sides. Y equals the square root plus or minus the square root of let's see here, 7, or x minus 7 divided by 6. And this would be the inverse function. And so that's how we solve for an inverse, is we just flip the variables and solve for y. Flip the variables, solve for f of x, and you'll end up with f negative 1 of x, which is the inverse of x. Another very interesting thing about inverse functions is their graphs. So I'm going to do a linear graph here. Let's go ahead and let's do a linear graph going through the origin here, and we'll do another linear graph going through the origin here. And we'll call this function here, we'll call this f of x, and we're going to set it equal to, let's say it's 3/2 x is this function. And now I want to solve for that function's inverse. So now our function is 3/2 times x. So how do I solve for the inverse? Well, I flip where the x's and the y's are. So instead of y equals 3/2 x, I now have x equals 3/2 y. Then I multiply both sides by 2/3 to get rid of the 3/2, and I end up with y equals 2/3 x. Well, this y that we solved for is in fact the inverse of f of x. And if we wanted to graph that, we would see that the rise over run is 2 rise per 3 run. It so happens to be that this other line that I drew is f minus 1 of x, the inverse of x. It's equal to 2/3 x. And with all inverses, what an inverse function does graphically is it takes the line y equals x. So y equals x is a line that's at a 45-degree angle to both the x-axis and the y-axis, and the inverse will always create a mirror image across that axis, that y equals x axis. And so, for example, if I had some graph that looked like this, if I took its inverse, I would mirror it across the y equals x line. And so that's graphically what's going on here. But how you find an inverse, you just flip the variables, solve for the new variable, the inverse variable, and then you'll get your inverse function. Alright, that's the first part, is inverses. And all you have to do to take a derivative of an inverse is to just take the inverse of f of x, and then take the derivative of the inverse of f of x, and that's how you take the derivative of inverse functions. Now next is logarithms. So I haven't made a video about e yet, or exponentials. So I'd like to go over a few things. So e to the x is one of the most interesting graphs, and the reason why is because e to the x is the only graph where the area under the curve is equal to the slope. And what I mean by that is here's our function e to the x that tapers off towards 0 as it gets further to minus infinity. Well, it turns out that the area under the curve to whatever point you're at on the graph is the same number as the slope at that point on the graph. So if we went to this point and it had a slope of, let's say, 2, the slope is 2, so the derivative at that point, x equals 2, the area underneath the curve all the way back is also equal to 2, and that has some very interesting implications. What that means is that e to the x is the only function that I know of where the derivative with respect to x of e to the x is simply itself. Now, this doesn't abolish the chain rule, for example. Let's say that I wanted to take the derivative with respect to x of e to the 2x. So you may think it's just e to the 2x. Well, that is the derivative of the outer function using the chain rule. So the derivative of the outer function is e to the 2x, but the inner function is what e is raised to the power of, which is 2x. So to satisfy the chain rule, we have to multiply our derivative of the outer function by the derivative of the inner function, which in this case, the derivative of 2x is just 2. And so we multiply that on. And you'll notice the pattern. If I take d dx of e to the x squared, what I'll end up getting is I'll get e to the x squared times the derivative of x squared, which is 2x. And so this would equal 2x e to the x squared. And that is how we take the derivative of e. What about natural log, right? As we know, the natural log of e is equal to 1, because natural log is defined as the log of which its base is e. And so, how do we deal with the derivatives of the natural log? The derivative with respect to x of the natural log of x is 1 over x. And this is just something that you're going to have to memorize. Once again, this works for every ln. This works for every natural log. However, the chain rule still needs to be satisfied. So if I have ln of x squared plus 5x, the derivative of this is the derivative of the outer function, or the ln function, which is going to be 1 over whatever's on the inside of the log. In this case, it's 1 over x squared plus 5x. But then to satisfy the chain rule, I must multiply it by the derivative of the inner function, which, using the power rule and linearity, x squared is 2x, and 5x, the derivative of 5x, is 5. So we multiply this on. The derivative of this whole thing is equal to 2x plus 5 over x squared plus 5x. And so just remember that the chain rule still applies with these, but the derivative of e to the x is e to the x. The derivative of ln of x is 1 over x, or 1 over whatever is inside the natural log function. Now, a great way to use this tool, there is a great way to use this. This is an algebraic tool, so for example, if I had a regular log, let's say I had a log base 10 of 3x, and I'm looking to take the derivative with respect to x of this. Well, we don't have any rules for logs that are not base e, or natural logs. But thankfully there's a trick called change of base. It's an algebraic trick where we can actually rewrite this in terms of natural logs. So the change of base states that I can write log base 10 of 3x as ln of 3x over ln of 10. So in other words, ln of the base number is in the denominator, and ln of the top expression is the numerator. Now, log of 10 is just a number, so we can actually pull that outside of the derivative, and we'll have 1 over ln of 10 times the derivative with respect to x of ln of 3x. And now we just have to take the derivative of ln of 3 of x, which is going to be 1 over 3x, because remember the derivative of ln of x is 1 over x. So the derivative of ln of 3x is 1 over 3x. But we still need to satisfy the chain rule, so we must multiply by the derivative of the inner function 3x, and that the derivative of 3x is just 3. So now we have this figured out this far. We have 1 over ln of 10 times 1 over 3x times 3. Well, the 3's cancel, and what you're left with is 1 over x ln of 10. And so these are how we can use the derivatives of natural logs and exponentials. I hope this was helpful. If you have any questions on it, feel free to shoot me an email. So I hope this helped, and I'll see you next time.